This morning we talked about Markov decision processes, and please remind that's a model that combines Markov chain and standard transition systems. So when we are in a state, then we have a non-deterministic choice between different actions, and for each of these state action pairs we have a distribution for the successor states. And please remind the one important thing what we also need now is that when talking about probabilities or expectations, then you need to consider a scheduler, which means a function that takes the history as input and returns an action or a set or distribution over the actions. So we come back at the end of the talk tomorrow in the morning. We talked about the computation of maximal expected mean payoffs, and now we return to another kind of expectation, namely accumulated rewards until reaching a certain goal. So this morning you have seen this picture here. We are given a weighted MDP, so an MDP with weights, integer weights for the state action pairs. And we have some distinguished state called goal, and we want to reason about the minimal or maximal expectation that we for the accumulated weight until reaching goal. Well, and this min and max, here we take the extrema over all schedulers. Now, to make sure that these expectations exist, we dealt with a rather strong requirement, namely that under each scheduler, the goal will be reached with probability 1. Well, and it is often the case if you start with a certain MDP and you want to reason about expected costs, max-min cost, that this condition simply doesn't hold, because there are schedulers where you will not reach the goal with probability 1. Well, and indeed, it has been discovered already a long time ago that you can relax the assumption. It suffices the existence of at least one scheduler where the probability to reach goal is 1, and then you can compute the minimal or maximal expectation, but now under all proper schedulers, and this notion proper means that you deal with a scheduler that reaches the goal with probability 1. And we ignore, for this min and max, we ignore the other ones. So let's have a closer look at this, and let's first observe that with this assumption here, we cannot guarantee that the maximal expectation is finite. So it is indeed a sup. If we take here the supremum over all schedulers, then this value can be infinite, and here's a trivial example for this. So here we have probability 1 for both transitions. So in state S, it's a non-probabilistic system if you want. In state S, you can choose action beta, in which case you earn the weight 1, and for action alpha, we have the weight 0. Now, if you look for the maximal accumulated weight, then it is indeed infinite, because there is a sequence of schedulers where the expected accumulated weight tends to infinity. And here we go. So consider sigma n to be the scheduler which schedules action beta, so this self loop here at state S, for the first n visits of state S, and for the n plus first visit of S, we go from S to goal via action alpha. Well, then by taking beta n times, we earn the weight n altogether. Well, and for the alpha, we get 0, so altogether under sigma n, the expectation is n. Well, now if n tends to infinity, then this means that this maximal expectation does not exist, or it is infinite. Now it has been shown by Bertsekas, someone from Greece here, Tsitsiklis. They have shown the following. So let xs denote the maximal expectation from state S. It might be infinite. Then they proved that if it's the case that for each improper scheduler, and by improper we mean one where the probability to reach the goal is less than 1, if each such improper scheduler enjoys the property that the expected total weight is minus infinity, then these maximal expectations for the expected accumulated weight until reaching G is finite for all states. And in this case, the vector with these expectation values is computable using the Bellman equations, what you have seen in this morning. So this means...
Can you show how this applies to the example?
Sorry?
Can you show how this applies to this example? This characterization, how does it apply to this example?
But it does not apply.
It does not apply.
Well, because the maximal expectation, here the statement is that the maximal expectation...
this is just one direction.
This is just one direction. It is just if. So, if for the example before, it means nothing. Well, just to remind, these Bellman equations, so if you are already in state S, then the expectation is 0, and otherwise the expectation is the max over all the actions that you can take in state S. Then the weight for the state action pair is alpha plus, and this is this weighted sum for all alpha successors T of state S multiplied with the expectation from state T. And with this assumption here, well, when you rephrase this equation system as a fixed point equation, then indeed it has this was shown, it has a unique fixed point, and, well, this is rather straightforward, this unique fixed point characterization also yields the existence of an optimal memoryless deterministic scheduler. And all this...
This does not apply when you only have positive or non-negative weights.
This one does not apply. Yeah.
Only if you have negative weights. Right?
Wait a second. What? This simply does not apply, but it is only an if-then. Well, and you can do value iteration, or you can rephrase the whole thing as a linear program. So the last few overlays were just what you have seen this morning. But now the question is how to compute XS in case that this condition does not hold, which means there is some improper scheduler where the expected total weight is not minus infinity, and how to check finiteness. So let's come to the following observation. Suppose first M is strongly connected, or we consider an end component of M. Then the maximal expectation inside M is infinity. Well, here I drop the state because it is infinite for some state if it is infinite for every state. If and only if E is weight divergence, which means there exists a family of schedulers such that you can increase the accumulated weight as high as you want using this sequence of schedulers. So which means that the supremum over all natural numbers R, where there exists at least one scheduler where eventually the weight is larger or equal R with probability 1. And this supremum should be infinite. Well, this is equivalent to the statement that there is at least one scheduler where the lim sub of the weights of the prefixes tends to infinity. So which means that there is some scheduler which makes sure that with probability 1 the weight gets very, very large. And this is the case if and only if either the maximal mean payoff inside E is positive, or it is 0 and E is gambling, and gambling means the existence of a scheduler such that almost surely the accumulated weight oscillates. So n tends on the one hand to plus infinity and the lim in to minus infinity. So it goes up and down and up and down and up and down. Well, now these two things, you have seen that computing the maximal mean payoff in strongly connected MDP, this is doable using a linear program. This can be checked in polynomial time. But what about this gambling condition? And indeed, it can be shown if you just start with an end component or a strongly connected MDP and you ask whether there is such a gambling scheduler. then this is an NP-hard problem. However, we only need it in combination with the assumption that the given end component, the maximal mean payoff is 0. And in this combination here is simpler, because then if you are given an end component where the maximal mean payoff is 0, then being gambling, let's say, if you pick some memoryless deterministic scheduler, either this memoryless deterministic scheduler is gambling, which is then the case, which achieves the mean payoff 0, which is then the case if this BSCC under such a scheduler has negative cycles, which again is equivalent to the statement that there are positive cycles. And the other option is that all BSCCs of such MD schedulers are 0 BSCCs, by which I mean that all the cycles, the accumulated weight is 0. And the trick to get this polynomial time algorithm is to identify all the end components which enjoy this property being a 0 EC in the sense that all the cycles have the accumulated weight 0. Well, and so in the end, to answer this question in the general case, what we can do is we can check this weight divergence for all the maximal end components using this criterion here and this polynomial time algorithm in case that the max mean payoff is 0. If this is not the case, if there is a weight divergence maximal end component, then indeed the maximal expectation from some states is infinite. If this is not the case, if there are no weight divergence maximal end components, then indeed the expectation for all states is finite, the maximal expectation, and we can generate a new MDP which satisfies these conditions such that all these techniques that are known from Berzekas, I'm sorry, that have been shown in the literature are applicable. Well, and how to get this? This is the technique I just checked. The major problem are so-called 0 ECs, where the accumulated weight along all cycles is 0. And what we do is, in case that all weights would be non-negative, then this is simple. Then you can just look for the sub-MDP consisting of those state action pairs that have 0 weight. And then you can identify the end components there and collapse them into a single state. So this MEC quotient I mentioned in the morning. However, if the weights can be positive and negative, it's not that easy. But what you can do is, I show this using this example here. So here these values, they are now not probabilities. Well, -2 is not a so good probability value. They are weights. So this would be, there are no probabilities at all, so which means every transition stands for probability 1 transition. Now, indeed, if you have a closer look at this area here, then indeed, whenever you take a cycle, let's say T, S, T, then the weight is -2, +2, 0, or go this way from V to U to T. So here we earn reward 3. Then -2 and -1, we also get 0. Now, what is a trivial observation about such 0 ECs? Whenever you pick 2 states, then every path has the same weight. And that's what we can use to come up with what we called a spider construction. We pick one reference state, here the state S. For all other states, yeah, well, they are, let's say, I omitted here the action labels. This is one action, and this is another action, and both of them have weight 1. Now what we do, we pick one reference state, here S in the example. And for all other states, here T, U, and V, we insert we throw away all other transitions inside this EC, and instead we have a single transition from each of these states to S with probability 1, and the weight is exactly the weight of all the passes inside this EC that go from T to S, which is here -2, or from U to S, which is here 0, or from V to S, which is here 1. And
what about the path that goes from V to S via T?
from
There is another way to go from V to S.
yeah, we ignore it because it has the same weight.
It happens to have the same weight. And
Because this is a zero EC in the sense that
okay.
all cycles have the total weight 0. And then this is a property that whatever path you pick between two states, they all have the same weight. And this is the weight we attach here. Well, now state S, well, as the reference state of this SEC, it keeps its own actions going outside. And you here, for instance, state T has a beta transition going somewhere else, not included in this AC. And so what we do is we simply move this transition from a transition from T to a transition from S. And the same here for state V. No, state V has nothing here. State U has a gamma transition, and this is now this gamma transition here. Well, and the thing we have to do is, for instance, for the beta, the weight of S beta is now the weight of going from state S to T, namely 2, plus the weight for the state action pair T beta. And so the idea is, whatever you can do inside this zero EC, you can mimic it here. Simply, if you start in another state, then we go to S. Let's say originally some scheduler might schedule here action beta for T. And what we do here is we go from T to S, and then we take the action beta, and the successors here are exactly the same as here. So in this sense, we can mimic the behavior, and I forgot to mention, for the incoming edges, we don't change anything. So this is the idea to, and well, this is now 1 0 EC, and you can repeat this process to eliminate them until all have been eliminated, or you have found a gambling EC, in which case the given MDP is weight divergence, and the expected accumulated weight is infinite. Now let's come now to the last part, which is about conditional probabilities and conditional expectations. Now, conditional probabilities, well, they are just defined using a quotient. So the probability for phi given psi is simply defined as the quotient for the event phi and psi divided by the probability for psi. Now, in case that we would deal with a Markov chain, then we do not have here some max or whatever. You can just deal with this quotient. Now, in a Markov decision process, let's look for instance, for the maximal conditional probability for phi given psi. Then we have here a max, or the supremum over all the schedulers, well, where of course the probability for the condition must be positive. Otherwise, this value makes no sense. Well, now the max for a quotient, you cannot simply put the max here to maximize the numerator and denominator separately. This makes no sense. Well, the technique that can be used is a transformation technique, so which starts with two events phi and psi and generates a new MDP, which depends on phi and psi, which is small in case that the properties phi and psi are simple ones. So I will explain the approach for the case where both are both are reachability conditions, such that this conditional maximal probability can be computed as the maximal probability in this new MDP, fairly for the same thing as here for the phi. This will be some modified formula. So how does this approach work? I will explain it for the case where both the objective and the condition are reachability constraints. So here the phi requires we want to visit eventually some set f, and the psi requires we want to visit g. So the first step is to generate some kind of
Suppose you did it just for Markov chain. How do you compute conditional probabilities for Markov?
Well, for Markov chains, there are several methods. You can either just compute the quotient, because there is no max here.
Yeah.
And there is another technique which in practice is often faster. There is a rescaling technique. You can you can drop some states where this probability is 0 for the condition, and for the remaining Markov chains, you can rescale the transition probabilities such that in the end you get a new Markov chain. The size is okay in case that the psi is not so difficult. If it's a reachability condition, then at most the state space doubles. And then whatever measurable event for phi you pick, you can compute the conditional probability as an unconditional probability in this modified Markov chain.
So we know, for example, there's just computing probability for LTL, let's say, is in this space, right?
Yeah.
What about conditional probability?
The same thing.
The same thing.
It's the same thing. Well, and the method I'm going to sketch here is also you can also apply it for Markov chains. So the first step is to generate some kind of normal form MDP, which fairly will do the following. It will ensure that you can consider F to be a subset of G. And for this we do the following. We start here with M, and we have here the set G, and here F. They might overlap. This doesn't play any role. Now in the new MDP, what we do is we add 3 trap states. So by trap, I mean a state without any outgoing transition. And whenever we visit a state in G, then we have a probabilistic choice to move to stop or goal with these transition probabilities. And the ratio behind this is as follows. As soon as you reached a state in G, which means that we have fulfilled the condition, and when we want to maximize the probability for eventually F given eventually G, then the best thing what you can do is to maximize the probability from this state to reach F. So we take here the maximal probability for this transition from G to goal. We take the maximal probability to reach F from this state G. And with the remaining probability, we move to this state stop. Now when we are, when we hit F, a state in F, then this needs some calculation, but the situation is similar. When you hit F, then the best thing what you can do is from there maximize the probability to reach G, and with the remaining probability we go to this state called fail. Well, and what is the intuitive meaning of fail? Here, when we reach this state, then this stands for the case where we fulfilled this objective, eventually F, but we failed to fulfill the condition, which means that with these conditional probabilities, these passes that go to fail, they should not count. Well, altogether, the soundness of this normal form transformation still yields that we have a conditional probability, but now we replace the eventually F over eventually G by the objective visit goal under the condition that we visit either goal or stop. And now the second step is the more interesting one. So we start now with this normal form MDP, and the idea is the following. All the probability mass of the passes that violate this condition, that do not eventually visit goal or stop, we want to redistribute their probabilities to the other passes. And the idea, so this is again this normal form picture with these trap states, stop, goal, and fail, is now as follows. As soon as we reached fail, then we simply introduce a new transition and reset. We try again. That's the idea. Now there might be some end components inside this MDP M prime, where you can also stay forever without visiting goal or stop. And we just do the same thing. We just introduce such a reset transition as an additional non-deterministic alternative. From whenever you are in such an end component, then you have the possibility to return to the initial state and to try again. Well, and the point is, we look here for the maximal probability, which means that taking these reset transitions from these end components too often makes no sense, because it does not help you to maximize these probabilities. So in the end, this construction indeed does the job, which means that you can compute this conditional probability as a standard maximal reachability probability in a slightly modified Markov chain. Now, this was the case for where both the objective and the condition are reachability constraints, but this is what we call the reset mechanism or reset method. You can lift it to arbitrary LTL objectives and conditions using automata, deterministic automata for both for phi and psi. And in the end, to answer your question that you did not yet ask, what is about PCTL star model checking with conditional probabilities, the same complexity theoretic results as it is known for the unconditional case. Now for Markov chains, as I just said, there are also other methods. You can simply compute this quotient, or you can, well, this rescaling technique. Typically, these are better than this reset mechanism, which you can also use for Markov chains. In practice, the reset method, in particular for things like value iteration, then convergence tends to get much slower than for the other techniques. That's fairly the reason. Well, and now the next observation is this reset method, now for MDPs again, it doesn't do the job when you want to reason about conditional expected accumulated weights until reaching the goal. And the point is, with each of these reset transitions, you might have accumulated weight when reaching this fail state, and then you return, but then you already have some accumulated weight. So that's why just applying this reset method does not help to reason about conditional expectations. So let's go back to this picture. So you saw that you can relax these requirements and just require the...
Every time you go back to the picture, you have to pronounce the name of the two of them.
Well, we saw that you can relax this requirement by just requiring the existence of a scheduler that reaches the goal with probability 1. And now let's relax it further. Just require there is at least one scheduler that reaches the goal with positive probability, which simply means, well, if you fix here some initial state, that the goal is reachable. And now we take all the schedulers which ensure that the goal will be reached with positive probability, and we look for the maximal condition expectations, or the expected accumulated reward until reaching goal, under the assumption that the goal is indeed reached. Before, I think it is never stated here on the slides, for this part I assume non-negative weights. So maybe the first question, why should we be interested? Is this just because I didn't find any other topic to to look at? Well, I claim this is a rather natural thing. So for instance, there is a lot of work on conditional expectation times for probabilistic programs, and if they also have non-determinism, then the underlying model is a Markov decision process. So the conditional expected number of steps until termination under the condition that the program terminates. But there are also several other reasons. So for instance, if you deal with some kind of resilient system which has some fault tolerance mechanisms, then you might be interested in zooming in exceptional cases that can appear, but they might not appear with probability 1. and look what happens then. So for instance, the conditional costs of repair protocols in such cases. Well, and also we found this notion in the literature, conditional value at risk. It also seems to fit with this conditional expectation. Well, remind for the unconditional expected accumulated rewards, you have seen that optimal memoryless deterministic scheduler exist, and they are computable efficiently using linear programs that have one variable per state. Now, in this conditional case, the world is completely different. Optimal schedulers might require memory, and you will see what I mean with that when we look at an example. Local reasoning is no longer sufficient. So look for this example here. So we have 5 states. We have 2 traps, goal and fail. And state S2 is the only one where we have a non-deterministic choice, either to take action alpha to go to goal, or to take this beta action. With one branch we stay in S2, and with one branch we go to fail. The reward values are stated here and are used here for this gamma transition from S1 to goal. This R is just a parameter, it stands for some natural number. Now let's look what happens under the memoryless schedulers. So suppose first we take the memoryless scheduler, which always takes action alpha in state S2. Then you can compute this maximal condition expectation as this quotient here. So indeed we just have, in this case, we have 2 successful passes, S0, S1, goal, in which case the accumulated reward is 1/2 times R. Or we have the option to go S0, S2, goal, in which case the accumulated reward is 0. This is this part here. And in this case, with probability 1, we reach the goal. So altogether, we get value R12. Now let's look for the other alternative. In state S2, we take action beta forever, and we ignore the alpha action. Then the probability to reach goal is simply 1/2. We only have this successful pass S0, S1, goal. Its reward is R, so we have here in the numerator we have R12, and in the denominator we have 1/2, so altogether we get a better result if R is positive. So action beta is better than alpha. But this is not the best we can do. Look for now it's a history-dependent scheduler, which chooses beta exactly for the first n visits of S2, and for the n plus first we take action alpha. Then the conditional expectation is given by this value here. So we have 2 options to reach the goal. Either this pass S0, S1, goal. So this is the same thing as you have seen before. And the other option is to go from S0 to S2, then taking this loop n times, and afterwards we take alpha and go to goal. And whenever we take this loop, we earn reward 1, which means altogether we earn here reward n. And yeah, well, these are these values. Now you can do some calculation, and you see that this equals this value here. And now if n is larger than r, then we get a value which is better than the value that we achieved for this memoryless scheduler beta, which was better than just choosing alpha. Well, and indeed, the optimal value is achieved if n is r plus 2. Now, what do we learn from this example? First, memory can be needed to achieve the maximum. In this example, in S2, we need a counter for the number of visits.
This is not a proof that memory is needed. Perhaps there is another strategy that randomly chooses between alpha and beta.
Yeah.
That's what you do. Yeah.
But this is the optimal. Yeah.
I believe it.
There are arguments, yeah. But you are right. Well, and the second thing, local reasoning is not sufficient, and this is the reason why I used here this reward parameter. In state S2, we saw that we need a counter, namely r plus 2, this was the optimal value. We need a counter to know how often we must take action beta and when we must take action alpha. But now, if you just look for state S2, then it depends, the optimal behavior depends on a reward value of this transition here, and this is even not reachable from S2. So that's what I mean. If you just look for the fragment that is reachable from S2, then we don't see this value R. So maximizing the conditional expectation is a global property, and local reasoning in this sense is not sufficient. Well, and there is another observation here. Altogether, the maximal conditional expected reward from the initial state S0 is finite. So it is this value here. However, if you look for state S2 and ignore the other states, just look for the reachable fragment, then from S2 it is infinite because, well, if you consider the sequence of schedulers that takes n time action beta followed by alpha, then we obtain these values here, but this tends, well, this one here equals n, so this tends to infinity. This is also something which does not apply in the unconditional case. Okay, so yeah, this is just to explain my notations. I'm going to use CE sigma, with sigma being a scheduler, simply means the conditional expectation from a given initial state. And I write CE max to denote the supremum over all the reasonable schedulers, and by reasonable I mean those that indeed reach the goal with positive probability. Well, the first thing we could prove, or let's say this was just to look at standard books on MDPs using well-known results for countable MDPs, we could prove that this supremum is achieved, but equals the supremum when we shrink the class of schedulers as follows. We only consider the deterministic ones and reward-based ones, by which I mean whenever you are in a state S, then you need not to remember the full history, just the value, the reward that has been accumulated so far. Well, and what has this to do with countable MDPs? You can unfold the whole MDP by just attaching the reward that you have accumulated so far and then looking at this countable MDP and ask the analogous question. And while using these results, then we get that this scheduler class, it's sufficient to consider these schedulers. This also answers your question why randomization does not help here. Well, now after some pre-processing, this is not stated on that slide, you can even start here with some set F and some set G here. There is some kind of pre-processing where in the end you can transform the given MDP into a new one that has exactly two trap states, goal and another state fail, as in the example. And with probability 1, under each scheduler, you will reach either goal or fail. So this is this after some pre-processing. Well, if this pre-processing has been done, then checking the finiteness of these maximal conditional expectations is easy. Namely, we can rely on this criterion here. The maximal conditional expectation is finite if and only if there is no scheduler such that the probability to reach the goal is 0, and under this scheduler you have some positive cycle. By positive cycle I just mean you accumulate the weight along that cycle, and if this value is positive, then that's what I mean here by positive cycle. Well, what is the ratio behind this? Maybe go back to the example. From state S2, this is infinite. And here we have this situation, the scheduler which only chooses beta. This one reaches goal with probability 0, and we have a positive cycle, namely this one. So this is and let's say here you can increase you can take this loop as long as you want, and from then on you move to goal. And that's the way how you can increase this conditional expectation as high as you want. So this explains if this condition is violated, then this one here must be infinite. Now, in case that we applied this algorithm to check finiteness and it was positive, then one can compute in pseudo-polynomial time an upper bound. At this stage, I do not claim anything else. It is just a safe upper bound. And we could prove that the threshold problem that asks whether the maximal conditional expectation is beyond some threshold. So this one here is just, it could be strictly larger or equal. This is one of these symbols. And the theta is some rational number, which is part of the input. This problem is p-space hard and p-space complete in the case that the given MDP is acyclic. Now let's look how to solve the threshold problem and how to compute the maximal conditional expectation. And the crucial observation was this one. There exists a saturation point, which means a natural number, which is the bound for the accumulated reward, from which on we can prove that optimal schedulers simply maximize the probability to reach the goal state. And if there are several such schedulers maximizing the probability to reach the goal state, then we pick one of them that maximizes the expectation. This latter part is computable in polynomial time. Well, and using this observation, we could design a pseudo-polynomial threshold algorithm for this problem here, for which we could establish this property. In case that the answer to this question is yes, then this threshold algorithm generates a scheduler satisfying either the condition that under this scheduler the conditional expectation is exactly theta, in which case this is already an optimal scheduler, or the conditional expectation under the constructed scheduler is strictly larger than this theta, if existent. So if the answer is no, then the algorithm returns no. Well, and using this threshold algorithm, we could design an exponential time algorithm to compute the maximal conditional expectation, and this is some kind of interleaving of some schedular improvement steps plus this applications of this threshold algorithm. How much time do I have? Still? Okay, so I can a little bit explain. So first, computing an upper bound. Well, when talking about conditional probabilities, I told you about this simple reset method in MDPs. Now, if the rewards are all non-negative, then one could say, okay, it's a safe over-approximation of the conditional expectations. If you apply this reset method, then whenever you do this reset, then you might have earned already some reward. So in the end, you increase the expectation. Yes and no. Yes, you obtain an upper bound, but the maximal expectation, if you do it in a naive way, it might be simply infinite. Now, for this new MDP that results after the reset mechanism, we want to make sure that the maximal expected accumulated reward is finite, which means that n does not have a weight divergent end component, or which means that through these cycles backwards from the failed state to the initial state, or some end component to an initial state, we do not want to introduce positive cycles. This is more or less the story. So what we do is we apply this reset technique in the end, but we refine the model M a little bit. We have the first mode where we simply attach the reward that has been accumulated so far, and we do this up to some bound, namely this one. So we sum up over all states, and we take the maximal reward for the state action pairs for state S. If we are beyond this bound, then we know that we must have seen a positive cycle. But if we have seen a positive cycle, then we know this is only possible under schedulers that reach the goal state with positive probability, which means that then you cannot have an end component. In particular, this cannot violate this weight divergence condition. And this is the trick from the second mode on, which means that we have reached this bound, then we simply have a copy of M. We simply simulate M without any reward annotations. And then we can do what you have seen before for the conditional probabilities. We simply have these reset transitions from all the failed states back to the initial state. And then you can, this one here gives you a safe upper bound for the maximal conditional expectation. Now a sketch of the threshold algorithm. It operates level-wise. So we first compute a saturation point, as I said, from which on we know how optimal schedulers behave. And then for this last level, the saturation point, we know the decisions of optimal schedulers. And then we go backwards to level, I don't know how to pronounce this symbol, let's call it rho minus 1, rho minus 2, and so on. Then we compute most feasible actions, and this being most feasible depends on this threshold theta for all the state reward pairs at this level, where we can reuse the decisions for the higher levels where we already computed, or where we already have made some decisions. And well, this is a standard trick to treat zero reward actions. In the end, we have, at this stage, we have some linear programming techniques. Now, to give you an idea for this most feasible actions, suppose we reached level R and we know the optimal decisions or good decisions for levels R plus 1 and so on, and all higher levels. So, and here we are, this is the initial state. We start with reward, accumulated reward 0. So here we have reward R, and this has happened with probability P. Now in state S, suppose we have two options. Either take this branch, the blue one, where we will from S visit the goal with probability Y, and the partial expectation would be theta, which means from S the conditional expectation would be theta divided by Y, and this theta divided by Z is the corresponding thing for another action. Now the conditional expectations for these schedulers, take this branch or this branch, they are given by these values here. So X, this means the probability to reach goal along some other passes that do not go through this configuration SR. And the rho is the corresponding partial expectation. Then this P is the probability to reach S with reward R. This is this factor here on both sides. And from then on, we have the R plus the probability to reach the goal plus the theta divided by, this is the, under this scheduler sigma, which takes this blue branch here, the probability to reach the goal. Well, and here we have the analogous thing. Now you can compute that or calculate that this, the left-hand side is larger than the right-hand side if and only if this value here is larger than the max of these two. Now here the R and the theta, the Y, the theta and the Z, these are the things that we can control, but this value here does not depend on the other values that we don't know when having considered the upper levels but not the lower levels. And so the idea is for the threshold algorithm, when we want to look for good decisions, most feasible decisions for level R, we take this value here, compare it with theta, and what we want to achieve is that these values here are greater or equal than theta. And this can be rephrased as a linear program. Well, I cheated here a little bit. We have such a thing for every state. So indeed, I should attach here theta s, ys, and so on. So altogether, this gives a set of linear constraints. And what we do is we use linear programming techniques to maximize this value, which then gives us this one here. And we can use the same observation to compute a saturation point. We know, well, this needs a proof, of course. We know that we first showed there is a saturation point. And from this saturation point, optimal schedulers simply maximize the probability to reach the goal, which means that we know the optimal behavior from this saturation point on, which means that we know these values, the theta and the y. That's what we fix. And then, well, to achieve this condition here, we want to make sure, or we look for a value r, such that this value here is larger or equal the maximal conditional expectations for all schedulers tau. Now there are two problems. This is the value we want to compute and that we don't know, but we are on the safe side if we replace it with an upper bound. Well, then we don't compute the optimal saturation point, but a valid one. And the next problem is all schedulers here, but here, well, this also needs a proof, but this is not that surprising. The Bellman equation, it does some kind of local optimization for every state. And that's absolutely the analogous thing applies here. It's sufficient to consider to fix this optimal scheduler here and just to look for the one-step variance. So you might move one step might be different from this chosen scheduler, but from then on you can plug in the values that you already know for that scheduler. So altogether, this gives you linear constraint, polynomially many linear constraints that you, and then you can seek for the smallest value r satisfying all these constraints. Well, and this how to compute the maximal conditional expectation. First, well, I hope you can read. Can you still read this? So this was this threshold algorithm, what we could prove what it does. In case that the maximal conditional expectation is indeed greater or equal theta, then it generates a scheduler such that either the conditional expectation under this constructed scheduler equals theta, in which case this is already a maximal one, an optimal one, or it generates a scheduler sigma where the conditional expectation is strictly larger than theta. Now this leads to the following rather naive idea to compute the maximal expectation. Pick an arbitrary scheduler, compute its conditional expectation, let's call it theta, and then run this threshold algorithm for this value theta. In case that you cannot improve the value, then you have found an optimal scheduler, and otherwise you repeat. And well, it picks some memoryless. Pick a memoryless. Deterministic. Well, as long as you can compute these values, this would be correct for any scheduler, but of course it makes sense to consider the simplest ones. Well, there is one problem that
this sounds like a little bit like policy iteration.
Yeah, this is some kind of policy iteration. Well, I called it here scheduler improvement.
How's it different from policy iteration?
Yeah, well, they do not have such a threshold. But I completely agree. It is in the same spirit. Yeah, I completely agree. Well, if we using this schema, then that's a valid algorithm, and eventually it will find an optimal scheduler. But the time complexity can be exponential, and to give you an idea why this is this green thing is the saturation point, and we considered all these levels. And at each level, we can have a memoryless deterministic scheduler. So altogether, in the worst case, what can happen, the number of iterations, at each level, we consider all memoryless deterministic schedulers. And in the number of memoryless deterministic schedulers is exponential. And the saturation point, well, the value is polynomial, but the logarithmic length is exponential in the size of m. That's what we could also guarantee. But altogether, this gives you something that is double exponential in the size of the original MDP. Now, we could do better, and again, we rely on this magic thing here. If this constraint, so consider a scheduler sigma, and if this constraint here holds, then sigma is optimal for level R. So what we do is, instead of just taking the conditional expectation of the last scheduler, we try to make bigger jumps. And what we do is we deal with these values as the threshold values of the threshold algorithm, and then one could prove that indeed an exponential number of schedular improvement or policy iteration steps is sufficient. Yeah, so this brings me to this was just to mention some more recent results, but now in summary, well, in the first part of this tutorial I talked about Markov chains, and the second part about Markov decision processes, and what you should keep in mind is somehow the fundamental problems is to compute reachability probabilities. In the case of Markov chains, these are linear equation systems. In the case of Markov decision processes, these are linear programs, or the iterative techniques, value or policy iteration. To reason about long-run properties, this requires reasoning about bottom strongly connected components in the case of Markov chains, and the analogous thing for Markov decision processes are these end components. And for mean payoff, this is not explicitly stated here. This is also reasoning about BSECs and this end component thing that I mentioned at the very end of the tutorial in the morning. So here we also have linear programs or linear equation systems. Well, altogether, probabilistic verification, at the very beginning in my first talk, I gave you some historical notes. So it started already 30 years ago, but it is still a very active research area, and there are many other things. So this field of weighted Markovian models, one counter, probabilistic one counter machines, and so on, and to look for algorithms that can treat with weight constraints. This is one area of research where there is a series of more recent papers. Then multi-objective reasoning. Well, what we considered in this tutorial, this was single objective in the sense maximize the conditional expectation or maximize the expectation or the probability to reach something. But you might have several objectives. You might, for instance, have two formulas, and you want to look for a scheduler that makes sure that the probability for the first formula is larger than 1/2, and for the second formula it is smaller than 0.3 or something like that. There are techniques for this multi-objective reasoning, and indeed they reuse ideas for this LP that I've shown you for the mean payoff games, at least to some extent. This is doable. There is a lot of work on parametric model checking for Markovian models. Well, there are various types of parametric, but one very active field is that instead of specify this in practice, this can be indeed a crucial problem. What are the probabilities, which probability values to attach at the transitions? Now, if you just can write there some parameters, p half, some expressions, and to obtain some closed formulas for reachability, probabilities, and so on, this can be very helpful. And indeed, for Markov chains, what you can get if you have such parametric transition probabilities, you obtain rational functions. For Markov decision processes, this is a bit more complicated, but this is an active research field. Well, then there is a lot to say about continuous time and even continuous space, so in the direction of probabilistic real-time or stochastic hybrid systems. There is a lot of research on stochastic games. Well, in MDP, you can consider it as a well, it is sometimes called 1.5 player game. So not the half is not a child, the half is the probabilistic player, and one player is the one who resolves the non-deterministic choices. But here by stochastic games, I mean here 2.5 players, so you have something like an MDP as game arena, but then you classify the states, which player makes a move or has to move. Well, there are various techniques to tackle the state explosion problem and various directions and how to apply these techniques in practice. Well, there is now also a series of tools, and probably the most prominent one is PRISM, developed at Birmingham and Oxford, which supports Markov chains, Markov decision processes, and also continuous time versions, also some kind of games, and also probabilistic timed automata. And it provides several engines to carry out the analysis, be it symbolic with Markov decision processes, not with BDDs, I wanted to say, MTBDDs, multi-terminal binary decision diagrams. Or this hybrid engine, well, it uses to represent the model, it uses this symbolic MTBDD-based approach, but when calculating probabilities or expectation vectors, it uses an explicit representation. Thank you.